Since we have some general information on ethers, next we're going to take a look at the preparation of ethers. One way is by the Williamson ether synthesis, and a second is alkoxymercuration demercuration. The Williamson ether synthesis involves an SN2 reaction between an alkoxide and an alkyl halide. So the alkoxide is the nucleophile. Oxygen will share its electrons with the R group of the alkyl halide, kicking out the halide as a leaving group, giving us this compound. Now, we spent a lot of time last semester studying SN2 reactions, and so review the mechanism and keep in mind the stereochemistry. For an SN2 reaction, remember that the nucleophile has to attack from the opposite face from where the leaving group is leaving. So we get inversion of configuration. Also keep in mind the competition between substitution and elimination. So in this first example, we have our alkoxide, and this is reacting with a primary alkyl bromide, and so this will attack here, kicking out bromine as the leaving group, which will give this connected to the CH2, CH2, CH3. So we have a new ether that is formed. But in our second example, we're using the same alkoxide, but this time we have a secondary alkyl halide. Think about substitution versus elimination when we have a strong base, such as an alkoxide, and this reacts with a secondary or with a tertiary alkyl halide. This is too crowded, and so rather than undergoing substitution, it is going to grab off a proton from here, giving us methanol and an elimination product. So the good news is this is a straightforward reaction that we studied a lot last semester, so this should be very familiar to you. And we even are familiar with the limitations. The bad news is this means that we are limited to methyl or primary alkyl halides. Remember, the structure of the alkoxide really doesn't matter. It's just the structure of the alkyl halide. Now notice with the Williamson ether synthesis, both reagents come from alcohols, because you can take an alcohol and treat it with HBr or PBr3, for example, to convert it to an alkyl bromide. And you can take an alcohol and you can treat it with a strong base to form the alkoxide. So we just saw a problem in terms of competition between substitution and elimination. But knowing that the structure of the alkoxide doesn't really matter, it's only the structure of the alkyl bromide matters, and knowing that both reagents come from alcohols, then you can decide which alcohol is going to be converted to the alkyl bromide and which one is converted to the alkoxide. So here, for example, we are looking at methanol and ethanol. And so our first option is that methanol can be treated with PBr3 and converted to methyl bromide. In our second option, let's say that ethanol is treated with PBr3 and converted to ethyl bromide. Let's say we are using a nice strong base such as sodium hydride, or it could be sodium amide. So this can grab off a proton, giving us the CH3, CH2O-. And now these reagents can be combined, and we will get the CH3, CH2O connected to the CH3. If we go the other direction, same thing here using sodium hydride, for example, then this will generate methoxide. And now when these reagents are combined together, the methoxide will become connected to the carbon that used to be connected to the leaving group. In this particular example, where we are trying to make ethyl methyl ether, it doesn't really matter which way we go. But what if we were trying to make, for example, isopropyl propyl ether? Well, in this case, we could use this as the alkoxide and this as the halide, or we could try this as the halide with this as the alkoxide. And what you'll notice is that here we should get a good SN2 substitution because we are reacting with a primary alkyl halide. But here we will not get substitution, we'll get elimination because this is a secondary alkyl halide. So be sure to consider the best approach of which alcohol should be converted to the alkoxide and which alcohol should be converted to the alkyl halide. In addition to the Williamson ether synthesis, another general and effective approach to make ethers is related to a reaction that we saw last chapter and possibly last semester. Remember, we saw that an alkene could be treated with mercury 2 acetate to form a mercurinium compound followed by an organomercury compound that contains both an OH and the mercury. And then sodium borohydride reduction would give us an alcohol. And in particular, this gives Markovnikov addition. Well, rather than carrying out this reaction in the presence of water, if we instead carried out this reaction in the presence of an alcohol, then this gives us a way to make an ether. This would again give us the mercurinium ion, where we've got this ring and this is still connected to the acetate. And then instead of adding water here, because we have methanol, then this is going to open up this ring to give the OCH3, and then here we still have the mercury connected to the acetate. And then with sodium borohydride reduction, that's going to replace this mercury with a hydrogen, giving us this compound. So it's a way to make an ether, and what you'll notice is that we effectively have Markovnikov addition, where the hydrogen becomes connected to the carbon that had more hydrogens, and the OR becomes connected to the other alkene carbon. So just a few different ways that we can make ethers.